Hello, this research title is an ACDC switch mode power supply based on half-bridge DCDC converter for low power applications, presented by Dr. Harith Al-Badrani from Nineveh University, Dr. Yasser Muhammad Amin, and Dr. Muhammad N. Abdul Qadir from the University of Mosul. The presentation parts are Introduction, Converter Topology, Mathematical Analysis, Simulation Results, Experimental Verification, and Conclusion. The switch mode power supply is also known as power supply, supply unit, regulated power supply, etc. is composed of a converter that converts electrical power efficiently using switching devices and using storage components like inductors or capacitors to supply power when the switching device is in its non-conducting state or off state. Switch mode power supply possesses high efficiency and is widely used in various electronic equipment such as LED lighting units, CCTV systems, stepper motor drives, medical equipment, and industrial instrumentation. The objective of this work is to develop and analyze an AC to DC isolated switch mode power supply with the following specifications. The input is an AC main system of 110 or 220 volts, subjected to fluctuations of -15 to +10%. The output voltage is adjustable in the range of 10 to 15 volts and the power rating is 250 watts. The switch mode power supply is composed of two sections, an AC to DC section followed by a DC to regulated DC section. To obtain isolation, a high frequency transformer is used which necessitates the addition of inversion and rectification stages. The first stage uses a single-phase diode bridge with capacitor voltage divider to obtain a DC output voltage for the next stage. To accept both 110 and 220 volts standards, the first stage has a selector switch. The capacitors provide two equal DC voltages. The DCDC has a half-bridge converter composed of a Q1 and Q2, a high-frequency isolation transformer, and two rectifying diodes D1 and D2, followed by LC filter stage. There is a small coupling capacitor, CC, between the switches and the primary side of the transformer. This capacitor prevents a flux from building up in the primary winding and causing the transformer to saturate. Analysis. Assuming continuous inductor current, the circuit operates in three states. In state 1, Q1 turned on. The positive V secondary 1 turns on D1. The voltages of the primary, secondary, and inductor can be defined as shown. In state 2, both Q1 and Q2 are off. The inductor current turns on D1 and D2. The voltages are defined as shown. In state 3, Q2 is turned on. The positive V secondary 2 turns on D2. The voltages of the primary, secondary, and inductor are defined. The operation cycle has 4 phases, timed to offer half-cycle symmetry. The duty ratio of a Q1 and a Q2 is denoted by delta, which ranges between 0 to 0.5. The primary side and inductor voltage waveforms are defined according to the earlier analysis, and both are affected by the capacitor voltage. The capacitor voltage is determined by the current and the capacitance. The average output voltage obtained by inductor voltage equilibrium equation shows that the output voltage is not affected by the capacitor voltage and determined by delta only. Simulation. The parameters given in this table has been selected to simulate the converter. The various voltage waveforms result from the simulation model are identical to their analytical representations obtained in the theoretical analysis stage. The current waveforms confirm the continuous inductor current assumed earlier and agree to their behavior described by the theoretical analysis. The converter has been implemented physically. The prototype is shown. The converter is controlled through a 16F877A PIC microcontroller. The AC supply is about 250 volts, 50 Hz. The first stage of the AC to DC converter was energized to produce a rectified DC voltage for the second stage converter. The switch mode power supply is operated at 31 kHz. Measured performance. The measured primary side voltage is shown. Compared to the waveform obtained by simulation, it is almost identical. There is a minor difference in the duty ratio, and this is due to the different AC supply voltage applied practically. The identical measured and simulated secondary voltage waveforms confirm the analysis presented earlier. Finally, the inductor voltage waveform agrees in general to the simulation results. However, it has a non-zero average due to the parasitic resistance that has been neglected in simulation. In conclusion, a two-stage AC to DC converter design was presented in this paper. Detailed theoretical analysis was performed. The mathematical analysis and simulation models have accounted for the effect of placing the flux reset capacitor between the primary winding of the transformer and the midpoint of the DC link. The results were validated by comparing the developed mathematical formulas to the simulation and experimental implementation. The presented switch mode power supply was developed for an output power of up to 250 watts. Thank you for your attention.